Okay. Bismillah ar-Rahman ar-Rahim. We'll do now 7.6 multiple eigenvalue solutions. Now we have the eigenvalues are repeated. Okay. So we'll start with some definitions. We say if k is a positive integer and we have this as a factor. So you have lambda 1 repeated as an eigenvalue repeated k times. We call this k the multiplicity. We call the eigenvalue lambda is multiplicity k. So they have this word, multiplicity k. You have an eigenvalue multiplicity k. We call it complete if what? If I can get k linear independent associated eigenvectors with this lambda, with this eigenvalue, then we call the eigenvalue complete. Yes, it's repeated, but still I can get k linear independent associated eigenvectors. We call it complete. Okay. I have eigenvalue multiplicity k, and we have exactly k linear independent eigenvectors, say v1, v2 up to vk. Then how I write the general solution? Right away, like what we did in the real distinct. K1, V1, the same lambda, X2, V2 since they are linear independent, until I reach XK, VK, E lambda, T. And they can have their linear combination. By the way, if you have diagonalizable matrix, then all eigenvalues are complete, no defect. What's the meaning of defect? I'll explain it later. Non-diagonalizable, at least one eigenvalue is defective. What's the meaning of defective? If it is not complete. If I cannot get k linear independent eigenvectors, I get less than k. I get p, which is less than k. And the number d, which is k minus p, then I have eigenvalue multiplicity k minus p, which is the linear independent eigenvectors I get. D k minus b, we call it defect of the defective eigenvalue lambda. Okay. Yeah, so an eigenvalue is complete if it is the dimension of the eigenspace equal to k, is equal to the multiplicity, which is the number of linear independent eigenvectors. Otherwise, we call it defective. The defect, as I said, this is the formula, multiplicity of lambda minus the dimension of eigenspace related with lambda. This is they call it the defect of an eigenvalue lambda. Let me do an example. Okay. How to solve this system? First, I'll find a minus lambda I. I'm looking for the eigenvalues. That give me what? 9 minus lambda, 4, 0, minus 6, minus 1, 0, 6, 4. No, sorry, this is minus lambda. This is 3 minus lambda. The usual things we are doing. I'll do the expansion with the last column. So positive, negative, positive, positive. I have 3 minus lambda. Yeah, let me do it quickly. 3 minus lambda. I cancel this, I cancel this. I have what? Yeah, let me do the product. Lambda square minus 9 lambda plus lambda. That will be minus 8 lambda. Okay. Minus 9 plus 24. Which is what? 3 minus lambda times lambda square minus 8 lambda plus 15. In other words, this is 3 minus lambda. What is this? Lambda minus 5, lambda minus 3. So I have lambda is 5, 3, 3. Okay. Then I have stated eigenvectors for each lambda. So for lambda equal 5, lambda 1. What I will do, I solve the usual system. Yeah, if you remember, lambda minus lambda, a minus lambda I times v1 now. I let v1, k1, k2, k3. The same thing which we did before. That give me what? 9, this is 4, 4, 0, minus 6. Yeah, minus 1, minus 5. minus 6, 0. 6, 4, 3 minus 5 minus 2 times K1, K2, K3 equal 0, 0, 0. So what we have? Yeah, I can divide the first one. Let me do Gauss elimination. Okay, it's Gauss elimination. So I have divide the first row by 1, by 4. I have 1, 1, 0, 0. This is by minus 6. I'll leave it. Who cares? That will not make a difference. 6, 4, minus 2, 0. Now do Gaussian, do the elementary row operation. Okay. Multiply by 6 and add 0, 0, 0, 0. Multiply by minus 6 and add, that will be 0. That will be minus 2. Okay. By minus 6 and add, that will be minus 2. So I have what? 1, 1, 0, 0, 0, 0, 0, 0. Divide by 1, by minus 2, I mean, 1, 1, 0. So actually you have what? You have K1 plus K2 equals 0, and K2 plus K3 equals 0. From this, I can get K1 equal minus K2, and from this, I get K3 equal minus K2 also. So my K2 is my free variables. Let K2 equal minus 1. I'm getting K1 equal K3 equal 1. So I have V1 will be what? 1 minus 1, 1. And what will be X1? My first solution, right away. 1 minus 1, 1, e to the power, what was my lambda? 5t. Okay. Now we'll come to the second case. Now for lambda 2 equal 3, where I have multiplicity 2. Huh? This is, we have multiplicity 2. Okay. I'll do the same thing. Huh? I let V2 will be K1, K2, K3, like what we did before. So I have A minus 3I V2, and this is equal to what? 640 minus 6 minus 40, 640 times K1, K2, K3 equals 0, 0, 0. Very clearly, I have only one equation. All three equations are the same. So I have 6K1 plus 4K2 equals 0, where I have K1 equal what? Minus 2 over 3 K2. How many free variables I have? K2 and K3. There is no restriction in K3. So I have 2 free variables. Okay. So we'll do this usual trick. Let K2 equal 1 and K3 equal 0. Not 1. I can do K2 equal 3. By 3, so that I have no fraction here. I can do, you can make it 1. It's up to you. And they let K2 equal 0 and K3 equal 1. That's the point. I let K2 a value and K3 0. Let K2 0 and the other K3 is a non-zero value. Since you have 2 free variables. Find K1 in this case. K1 will be what? Yeah, 2. K1 will be 2. In this case, K1 will be 0. What will be V2? I have 2. Oh, sorry, this is minus 2. It's minus 2, 3, 0. And V3, I have 0, 0, 1. So I have 2 linear independent eigenvectors. So that means, what will be the defect for this lambda? For lambda, what was the lambda? 3. Lambda 2, which is equal to 3. It's, if you remember, multiplicity minus the dimension of the eigenspace. The multiplicity 2 and the dimension is 0. So no defect. So lambda 2 is a complete eigenvalue. That means, what will be my solution? X2. Write the first eigenvector, e to the power, what was lambda? 3t. And x3, the other one. What will be my general solution? I have now 3 solutions. X will be C1 x1 plus C2 x2 plus C3 x3. That will be my general solution. I just list them. Okay. Now this is, yes, I have multiplicity, but when I find the eigenvectors, I find the same number of eigenvectors as the multiplicity. That will make it easier. Now let me move to the case if I had multiplicity 2, lambda is an eigenvalue multiplicity 2, and there is only one eigenvector. So D will be K minus B, it will be D minus 1, which is 1. So you have defect is equal to 1. What to do? This is the algorithm for eigenvalues with multiplicity D and defect 1. Find the eigenvalue, we did. Multiplicity 2, this is, first we'll find the eigenvalue. We compute this, A minus lambda I to the power D plus 1, which means A minus lambda I all square. Then find the non-zero vector. Find the non-zero vector related to this, which is equal to 0. Make this times U1. This matrix, A minus lambda I all square times U1 equal to 0. Not only that, and A minus lambda I times U1 not equal to 0. That U1 multiplied by A minus lambda I, we get U2. Then we have this form. My first solution, U2 e to the power lambda t. My second solution, U2t plus U1 e to the power lambda t. Let me do an example. 2 by 2, easy one. Okay. So we'll find now the eigenvector. What you have? The eigenvalues, I mean. 1 minus 4 minus 3, 3, 7, 1 minus lambda. I saw 4, so I write 4. Okay. 7 minus lambda. That will give me what? Lambda square. Minus 7 lambda minus lambda minus 8 lambda plus 7 plus 9. And that will be lambda square minus 8 lambda plus 16, which is lambda minus 4 all square. So lambda 4 and 4. So I have multiplicity 2. Lambda equal 4, multiplicity 2. Okay. Now for lambda equal 4, I have only one lambda. Okay. I'll solve the system. A minus 4i times V1. And that will be what? 1 minus 4, that is minus 3 minus 3, 3, 3 times K1, K2 equals 0, 0. So that gives me minus 3K1 minus 3K2 equals 0. This equation is the same. I'm getting what? I'm getting that K1 equal minus K2. So how many eigenvectors we have? 3 independent eigenvectors. We have only one. You have only one free variables. Free variables is only K2. So that we have only one linear independent eigenvectors, which is just, I will find it just to tell you something later. That will be, I will write K1, 1, that will be minus 1. Yeah, I write K2, 1. Sorry, it's okay. Both are correct. K2, 1, and this will be minus 1. That will be an eigenvector. So I have only one. So D, which is K minus B, it will be 2 minus 1, which is 1. So I have eigenvalue, multiplicity 2, and defect 1. So I will follow this procedure. Okay. So you have the case, multiplicity 2, and defect 1. Okay, let me do the, we'll follow the procedure step by step. Okay, so my step 1, do what? Find A minus lambda I D plus 1. Okay, which is D equal 1, so I have I minus lambda I square. That is what? Just the multiple, just multiply this. So I have yeah, my lambda is 4, huh? My lambda is 4. So I have minus 3, 3 times minus 3, 3. Do the calculation, you get what? 9 minus 9, 0. 9 minus 9, 0. Minus 9 plus 9 is 0. So this is step 1. We find this. Step 2. Find U, then 0. U1 equal to U2. We call it U1. Okay. Where, be careful here. A minus lambda I U1 square equals 0. But I need another condition also. A minus lambda I U2 not equal to 0. So I need the two conditions. Okay. Now if you want to solve this A minus lambda I square, I'm doing it in details. U1, this is 0, 0, 0. You let U1 as usual, K1, K2, or V1, or call it the way you like. This will be what? Nothing. I have 0 equals 0, no restriction. So what are the free variables? Everything is free. I mean, I have no restriction, K1, K2. So I can check, let U1, 1 and 0, for example. Easy ones. You need to be sure. You need to be sure before you proceed. For sure, it will satisfy this, satisfy the first condition, since actually any vector can satisfy this because this is 0, 0. I need to check also, check A minus lambda I times U1. That should not be equal to 0. Check it. That is minus 3, 3, 3. Well, U1 is what? We choose it to be 1, 0. Somebody will say 0, 1, 3, 0, 3, 1. It's up to you. Do it the way you like. This one will get what? Minus 3 and 3. Not equal to 0. So this U1 is okay. Satisfy these two conditions. This condition and this one. Done. Then I will find U2. Find U2. It will be what? A minus lambda I U1. Just applying the formula. This is equals A minus lambda I U1. Do the calculation. Actually, I did it. It's minus 3 and 3. Huh? Actually, I'm finding it here. It's minus 3 and 3. By the way, if you notice, this one, which is U2, is a scalar multiple of your eigenvector for the matrix. Just for your information. This is some kind. Sometimes it's good to use it as a checkpoint. Okay. Now we'll find the solutions. X1 will be, what is it? U2 E lambda T. U2 E lambda T. And that equal to, what is U2? This is my U2 minus 33 E40. X2. Apply the formula. That's it. The formula is saying what? U2T plus U1 E lambda T, which is equal to what? U2 is what? Minus 33 times T plus U1. What is U1? I chose it 10 times e to the power 40. that will be what? Minus 3t plus 1 and 3t times e to the power 40. That's it. So my solution, my general solution, x will be c1 x1 plus c2 x2, and that equals c1. What is x1? X1 is this one. Put it there. Plus c2. What is x2? This is x2. Which is the same as this answer. Exactly. So I get now the solutions. Just I followed I followed the algorithm. I think it's very easy to follow. Okay. Now I have the second case. What we have here? We have multiplicity 3 and defect 2. It means what? I'm getting only one eigenvector. Only one linear independent eigenvector. So D will be 3 minus 1, which is 2. What is the algorithm? I'll find, this is step 1, the same thing. I'll find where I have a minus lambda I, my D is 2 in this case, which means I'll find a minus lambda I all cubed. Then I'll find a non-zero vector, u1, so that a minus lambda I cubed times u1 is 0, but the one before it, a minus lambda I square times u1 not equal to 0. Done. I find u1 right away. u2 is what? A minus lambda I times u1. u3, a minus lambda I, u2. Then for sure you will see u3 is an eigenvector of A, or a scalar multiple of it, like what happened here. When I find my eigenvector, I find that u2, the last one, is a scalar multiple of that one. What will be the solutions? Right away. First solution, u3, the last one, e lambda t, and then u3t plus u2, e lambda 2, e lambda t for u2, and then half u3t squared, like of the expansion of the series. I have tn over n factorial, and so on, u2t plus u. Let me do this example. Yeah, maybe it's better. Calculation will be easier. So I have a minus lambda I, that will be minus 1 minus lambda, 0, 1, 0, 1 minus lambda, minus 4, 0, 1, minus 3 minus lambda. That will be what? Minus 1 minus lambda. I do the expansion in the first column, which is easy, times what? Now, the determinant of this, which is what? Let me do the calculation right away. Lambda square, 3 lambda minus lambda, plus 2 lambda, minus 3 plus 4. Yeah. So I have minus 1 plus lambda. I have here lambda square plus 2 lambda plus 1, which is lambda plus 1 all square. So I have lambda minus 1 minus 1 minus 1. So I have multiplicity 3. Multiplicity. Multiplicity 3 for lambda equal minus 1. Now we'll find the eigenvectors, see what will happen. Which case? So find the eigenvectors. So I will do A minus lambda I times V1 is equal 0. So I have what? Minus 1 minus minus 1, that will be 0, 0, 1. Okay. 1 minus, that will be 2, minus 4, 0, 1, minus 1, minus minus 1, that will be minus 2, times K1, K2, K3, equals 0, 0, 0. So I'm getting what? I'm getting K3 equals 0, is the first equation, and K3 equals 0. And I have 2K1, 2K2 minus 4K3 equals 0. And K2 minus 2K3 equals 0. From this, I'm getting K2 equal to K3 equals 0. So what is my free variables? I have only one free variable, which is K1. So my V1, I let K1 equal 1. So my V1 is 1, 0, 0. So we have only one eigenvector. So D will be what? K minus P, and that will be 3 minus 1, which is 2. So I have this case. I have multiplicity 3, and the defect D equal what? 2. So it means I need first to find what? A minus lambda I cubed. So let me find A minus lambda I cubed. See what will happen. It will be minus 1, 0, 1. No. This is equal to what? So we'll do A minus lambda I square first. So multiply this matrix 0, 0, 1, 0, 2 minus 4, 0, 1 minus 2 by itself. See what I'm getting. This times this, that will be 0. This times this, that will be 1. This times this, that will be minus 2. Okay. This times the first column, 0. This 0, 4 minus 4, that will be 0. 0 minus 8 plus 8, that will be 0. Then the third row, that will be 0. 2 minus 2, 0. Minus 4 plus 4, 0. What will be A minus I cubed? That will be this matrix times the square, which is this one. 0, 1 minus 2, 0, 0, 0, 0, 0, 0. I'm getting what? This one, 0. First row times second column, 0. Times third column, 0. This one, 0. This one times the second column, 0. Times the third column, 0. And the same thing with the last one. I'm getting 0, 0. So we need to find U2. What do you call it? What is the name we call it? No, not this. We call it U1. You call it U1, U3, it's up to you. Find U1 such that what? A minus lambda I U1 minus lambda I cubed is equal to 0, but A minus lambda I square times U2 times U1 not equal to 0. You can choose U1 any value from this, since this is 0, 0, 0, 0, 0, 0, 0, 0, 0 times K1, K2, which is true for any K1, K2, K3. So choose U1 to be 1, 0, 0. I'm not sure that will work or not. What I will do, I will check it with this matrix. CA minus lambda I squared times U1. That will be 0, 1 minus 2, 0, 0, 0, 0, 0, 0 times this times U1. You will get what? This, that will be 0. I'm getting 0, 0, 0. So that will not help. That choice is not correct. That will not help me. I don't want it to be 0. I want this not equal to 0. Usually we do this. Choose another one. Don't make it complicated. Oops. Choose this 0, 1, 0. Are you sure that that will not work? Yeah. Choose 0, 1, 0. See what will happen. 0, 1, 0. You will get what? Now check A minus lambda I square times U1. That give me what? 0, 1 minus 2. You can choose any, but be sure when you multiply it by U1, you should not get 0. That will be what? Multiply this by this, I'm getting 1. Good. The rest is 0. It's multiplying the row by 0. So that's not equal to 0. So this choice is a good one. The previous one does not work. I think I need more space. Okay. Then what I will do, now we find U1. Satisfying this, not this. Okay. Then I will go to U2. U2 will be what? A minus lambda I U1. What is A minus lambda I? A minus lambda I, where is it? It is 0, 0, 1, huh? 0, 0, 1, 0, 2 minus 4, 0, 1 minus 2. Am I right? Yes. Multiplied by U1, which is 0, 1, 0. That give me what? This times this, 0. This times this, 2. Yeah. The third row, with the first, with the column, it will be 1. That will be U2. Then we'll find U3, which is A minus lambda I U2. That will be same times U2. This is U2. 0, 2, 1. That give me what? First column, that give me 1. The second column, 4 minus 4, that is 0. The third row, I mean the second row times the column, it will be 0. Third row times the column, it will be 2 minus 2, which is 0. Notice this is 1, 0, 0, which is the same as my eigenvector or a scalar multiple vector. This is checkpoint. This is should be scalar multiple of my eigenvector. Or times 1. Yeah, this is scalar multiple, including times 1. Right away. Now the solutions. Solutions. I get everything now. Solutions. Y1, U3, A lambda. Y2, second solution. U3t plus U2, A lambda t. And this is the third solution. Half U3t squared plus U2t plus U1. That's my first solution. U3, A lambda t. And that 1, 0, 0. What is lambda? Lambda was what? Minus 1. Lambda minus 1. Yeah, minus t. X2, U3t plus U2 times E lambda t. What is U3? 1, 0, 0. U2, 0, 2, 1. Don't forget you have t here. All of this times E minus t, which is equal to what? T, 2, 1 E minus T, which is this one. And this is my first solution. Exactly the same. X3 will be half U3 T squared plus U2 T plus U1. And that equal to what? Yeah, be careful. I have half here. What is U3? 100 times T squared. U2 021 times T. U1 010. All of this times, don't forget, E lambda T. E minus T. That will be what? T squared. Then I have half T squared, sorry. Half T squared. Here I have 2T plus 1. And the last one will be T. Times E minus T. Which is half T squared 2T plus 1T. My general solution, X will be C1 X1 plus C2 X2 plus C3 X3. The next one is this case. Let me do one example at least. So I have all the three cases. Eigenvalues, multiplicity 3, and defect is 1. Defect is 1. So I have how many eigenvectors? We have 2 only. Sorry. We have only 2 eigenvectors. So D will be K minus B, which is 3 minus 2, which is 1. What's the algorithm? To do that, find 2 linear independent eigenvectors, V1 and V2. Since I have 2 eigenvectors, so I'll find 2 linear independent eigenvectors, I mean. Then you compute this A minus lambda I, D plus 1, the square, since I have D equal 1, up to square. Do the same trick, U square. I need times U1 to be 0. And where A minus lambda I times U1 not equal to 0. You compute U2. This, like in the case of real distinct, the first 2 solutions. The third one, you do it with the T, U2T plus U1, A lambda T. That will be the case. Let me do this example, see what will happen. Okay, so I have A minus lambda I. That will be what? Minus 2 minus 9. I'm sorry. Minus 2 minus lambda. Minus 9, 0, 1. 4 minus lambda, 0, 1, 3, 1 minus lambda. Very clear. I'll do the expansion with the third column. That will be 1 minus lambda plus minus plus minus plus. So it's where it will be plus 1 minus lambda. Yeah, and I need this block. No, sorry. I need cancel the third row and the third column. So I need this block, which is what? Lambda square minus 4 lambda plus 2 lambda minus 2 lambda minus 8 plus 9, which is 1 minus lambda times lambda square minus 2 lambda plus 1. This is the common, yeah, very clear, lambda minus 1 all square. So I have lambda, let me write it here, 1, 1, 1. So I have multiplicity 3. Find the eigenvectors. I find A minus lambda I times V1 times the eigenvector, okay? What you have? Minus 2 minus 1. That will be minus 3 minus 9, 0. Have 1, 3, 0, 1, 3, 0 times K1, K2, K3 equals 0, 0, 0. So you have what? What are the equation? Minus 3K1 minus 9K2 and K1 plus 3K2 Same. Very clear to me, all these three equations are the same. So I have K1 equal minus 3K2. So how many free variables they have? 2. Because there is no restriction in K2, and also there is no restriction in K3, which is K2 and K3. So I have V1 will be what? Yeah, I will do this trick. So I'll do the trick. Let K2, I have what are the free variables? K2 and K3. K2 equal 1, and K3 equal 0, and K2 equal 0, and K3 equal 1. What will be K1 in this case? K1 will be minus 3. And my first eigenvector, it will be minus 3, 1, 0. Now what will be K1 in this case? 0, since K1 depends only in K2 and K2 equals 0. So my eigenvector will be 0, 0, 1. Now I need to find U2. Okay, keep these things later. Okay, now we did this. We find V1 and V2, خلاص. Now I need the U1. What is the defect? 1. So I need A minus lambda I. A minus lambda I to the power 1 plus 1 square. That will be what? To the matrix square. So I have minus 2. Yeah, minus 3 minus 9. 0. 1, 3, 0. 1, 3, 0 by itself. See what you will get. The first row times the first column. You have what? 9 minus 9. That will be 0. Yeah, the first row times the second column. 27 minus 27. That is 0 also. And the third column is 0, 0. So you have nothing. 0. Same thing. 0 minus 9 plus 9, 0, 0. This is will be the same. So find, we call it what? We call it U1. U1 such that A minus lambda I square U1 equals 0, but A minus lambda I U1 not equal to 0. From here, I have no restriction. U1 can be anything. So choose U1 as usual, 1, 0, 0. You can choose 0, 1, 0, 0, 0, 1. It's up to you. But the most important, I need to check this. Note A minus lambda I. Where is A minus lambda I? It's, so I need to check minus 3, minus 9, 0, 1, 3, 0, 1, 3, 0 times U1. What you will get? You will get minus 3, this row and this minus 3, 1, 1, not equal to 0. So I can choose U1 is this. What will be my U2? U2 is this things, which I'm getting. That will be U2. A minus lambda I times U1, which I did. So U2 will be minus 3, 1, 1. That will be my U2. Okay, solutions. X1, V1, A, what lambda? T, A lambda T. What is V1? V1, V1, where is V1? Yeah, this is V1. Minus 3, 1, 0, 80. X2. V2, since you have two linear independent eigenvectors, A lambda T. And that, what is V2? 0, 0, 1, 80. Third solution. Yeah, here you need to be careful. That will be my third solution. U2T plus U1 E lambda T. U2T, let me write the formula, plus U1 E lambda T. And that equal to, what is U1? Yeah, U1 is 100 T plus U2. It's U2, not U1. Yeah, U2, sorry. I start with U2, not with U1. U2, which is minus 311. Yeah, times T plus U1. What is U1? 100 times ET. Lambda is 1. That will be what? Minus 3T plus 1 T T ET. Oh, sorry. What is my general solution? X will be C1x1 plus C2x2 plus C3x3, where x1, this one, correct, x2, this one, correct, and x3 plus 1. Yeah. I will stop the recording. I think now we did good number of questions. Let me stop the recording. Thank you.